8 worlds, 1 star, and endless calm between them, the solar system is full of quiet wonders that can lull even the busiest mind to rest. Tonight we'll drift through the most relaxing facts about our cosmic home. If you enjoy peaceful journeys like this, please like, subscribe, and share, and tell us in the comments which planet feels the most calming to you. Thank you for watching. Now let's begin. At the farthest reach of the sun's influence, the solar system fades into the quiet density of interstellar space. Here, beyond the orbits of the planets, beyond even the most distant icy worlds, a vast invisible frontier unfolds. The region is called the heliosphere, the immense bubble carved by the solar wind, a stream of charged particles that flows outward from the sun in all directions. Over billions of kilometers, this wind expands, carrying traces of the sun's magnetic field. As it travels farther, it weakens until it meets the thin plasma between the stars. That boundary, known as the heliopause, marks the true edge of the sun's domain. The solar wind slows, they're compressed by the pressure of the interstellar medium. Between the two lies a transition zone called the heliosheath, where the solar wind becomes turbulent and slows almost to rest. Beyond that limit, the particles and magnetic fields of the galaxy dominate, drifting silently through the vacuum. This edge is not a wall, but a gradient, a slow blending from one environment to another. Inside it, the influence of the sun is still measurable: radiation, magnetic fluctuations, and charged particles that trace back to the solar surface. Outside it, a new realm begins, filled with particles born in other stars, moving at different speeds and directions. The two flows meet in a delicate balance. Spacecraft that have traveled this far, such as Voyager 1 and Voyager 2, have crossed that invisible border. Their signals, faint but steady, reveal how the solar wind diminishes and how cosmic rays from beyond the galaxy increase in strength. The temperature drops. The density of particles rises slightly. The environment shifts from solar to interstellar, from the rhythm of one star to the background of many. The scale of this region is immense. The heliosphere stretches for tens of billions of kilometers, forming a shape somewhat like a teardrop, elongated in the direction opposite the sun's motion through the galaxy. The leading edge, where the solar wind meets the oncoming interstellar gas, is compressed and dense. The trailing edge flowing behind the sun extends farther, thinning into a long wake. Within this bubble, the solar system moves together through space, wrapped in a magnetic shell that shields it from much of the cosmic radiation beyond. That protection is partial and uneven, but it has shaped the conditions under which planets and life evolved. Without it, the energy from distant cosmic events would reach the inner planets in much greater intensity. In this distant place, the sense of movement is slow. The solar wind, still traveling hundreds of kilometers per second, expands outward into almost perfect silence. There is no sound, only the faint pressure of particles drifting through an immeasurable void. The density here is so low that the average distance between atoms can be measured in the length of football fields. Yet even this sparse environment has texture. Magnetic fields twist and reconnect. Energetic particles spiral along invisible lines of force. Occasional shocks from solar flares or coronal mass ejections ripple outward, passing through the region like distant waves on a calm sea. When they reach the edge of the heliosphere, they stir its boundaries briefly before fading into the interstellar background. The heliosphere itself is not fixed in size. It expands and contracts as the sun's activity rises and falls through its 11-year cycle. When the sun's magnetic field is strong and active, the heliosphere inflates, pushing its boundary farther into space. When the field weakens, the bubble shrinks slightly, allowing the galactic medium to press inward. This slow breathing motion changes the exposure of the planets to cosmic rays, altering how many energetic particles reach the inner solar system. On Earth, Subtle variations in cosmic radiation can be detected in the upper atmosphere, recorded even in the chemistry of ancient ice. These rhythms trace back to this distant frontier, showing how connected the entire system remains. Beyond the heliopause, the environment belongs to the galaxy. Interstellar plasma dust grains and magnetic fields drift together in a mixture that fills the space between stars. The Sun, like other stars, carries its own shell of influence as it moves through this galactic sea. The relative motion between the two mediums forms a bow-shaped structure ahead of the heliosphere, similar to the wake of a ship moving through calm water. This region, called the bow wave, marks where the Sun's forward motion compresses the interstellar gas. It glows faintly in infrared light, though too dim to be seen with the human eye. Instruments aboard deep space probes have measured traces of this boundary, revealing its gentle asymmetry. Even at this distance, the Sun's presence is not gone. Light from the solar photosphere still travels outward, though it grows faint against the darkness. A photon that leaves the Sun will pass this boundary in less than a day, moving at the constant speed of light. Particles, however, take years to cross. The voyagers travelling at tens of thousands of kilometres per hour required more than 4 decades to reach this place. Their instruments now sense the interstellar medium directly. The data they send back, faint and delayed by billions of kilometres, offer the first true measurements of conditions beyond the solar system. The signals themselves are whispers, tiny fluctuations in radio waves that carry across the light years back to Earth. Within this quiet frontier, energy and time flow on different scales. The space beyond the heliosphere is not empty, but filled with the memory of stellar generations. Every atom there was once part of a star expelled into the galaxy by ancient explosions and stellar winds. The Sun and its planets move through this environment, much as a leaf drifts through air, guided by larger forces but following its own slow path. From this boundary, looking inward, the solar system would appear as a small bright domain surrounded by darkness. The orbits of the planets would be hidden within a pale glow of scattered sunlight, a faint sphere shining against the void. If one could hover here beyond the heliopause, the Sun would still be a star among many, bright but not unique. Its light would blend with the background glow of the Milky Way, its warmth too weak to feel. Around it, the unseen bubble of the heliosphere would continue to drift, protecting the planets as they follow their orbits. The silence would be near absolute. Only the constant movement of charged particles, the slow vibration of magnetic fields, and the steady flow of time would mark the passage of anything. This region, though distant and almost empty, defines the solar system's outermost breadth. It is where the energy of one star finally yields to the broader rhythm of the galaxy. The transition is neither sudden nor sharp. It is a soft gradient that connects two great domains, the influence of the Sun and the reach of interstellar space. In this balance lies the quiet structure that surrounds everything closer, in shaping the journey of light, dust, and magnetic fields that move inward from the cosmic background. From here the solar system begins, and from here its story flows gently toward the Sun. Beyond the edge of the heliosphere, the solar system continues in forms that cannot be seen but are still held by the Sun's faint gravity. The Oort cloud lies there, a distant spherical reservoir of ice and rock that marks the outermost extent of the Sun's influence. It is not a continuous shell, but a population of billions of small frozen bodies drifting through space at immense distances, perhaps as far as 100,000 astronomical units from the Sun. That distance places them nearly halfway to the nearest stars. Each object circles the Sun so slowly that its orbit may last millions of years, completing only a single revolution since the formation of the solar system. In this realm, sunlight is more than a whisper. It is a pale trace indistinguishable from the starlight that fills the galactic night. The materials that form these distant objects are remnants from the birth of the planets, preserved in extreme cold. Water ice, methane, ammonia, and carbon compounds are mixed with dust and rock, forming compact nuclei no larger than mountains. They remain frozen undisturbed until a passing star or the tidal force of the Milky Way perturbs their orbits. When that happens, a few ascent inward, beginning journeys that may end as comets visible from the inner solar system. The Oort cloud is a boundary between belonging and drifting away. Its outermost parts may already blend with the gravitational domains of other stars, creating overlapping regions where no single system has full control. The objects there are relics of a time when the sun was young and still surrounded by a dense cloud of gas and dust. During the early chaos of planetary formation, many icy planetesimals were scattered outward by the growing giant planets. Some escaped entirely into interstellar space, but others slowed just enough to remain gravitationally bound. Over billions of years, these survivors formed the distant shell that now bears the name of the Dutch astronomer Jan Oort, who first inferred its existence in the mid-20th century. His reasoning came from the orbits of long-period comets, bodies that approach the Sun from all directions not confined to the flat plane of the planets. Their random inclinations and extreme distances suggested a vast spherical source, invisible yet real. Though never observed directly, the Oort cloud's presence is supported by statistical evidence. Each long-period comet that enters the inner solar system carries information about this hidden population. By tracing their trajectories backward, scientists estimate the scale and shape of their source. The inner part of the cloud, called the Hills cloud, may be denser and closer, perhaps around 10,000 astronomical units from the Sun. Beyond it, the outer Oort cloud stretches into the dark until the Sun's gravity finally weakens to insignificance. The density of objects decreases sharply with distance, but because the volume is so enormous, the total number remains vast, perhaps trillions of icy fragments drifting through cosmic night. The environment here is almost motionless. Temperatures hover only a few degrees above absolute zero. Radiation from the galaxy passes freely, but the energy is too faint to change the frozen chemistry of these bodies. Collisions are extremely rare. The distances between objects are measured in billions of kilometers. Over eons, gentle gravitational tides from passing stars and from the collective pull of the Milky Way slowly reshape the cloud. It may oscillate slightly as the solar system moves through the galactic plane, breathing in and out over tens of millions of years. The process is slow and without sound, a movement that registers only across geological and cosmic timescales. When one of these distant bodies begins its inward fall, it changes gradually from an invisible particle of the outer dark to a visitor of the inner system. At first, it moves imperceptibly faster, its long arc curving inward as it surrenders to the Sun's gravity. Thousands of years may pass before it reaches the realm of the giant planets. As it nears the Sun, sunlight grows stronger, warming its surface and releasing gas and dust. The material forms a coma and tail, turning a silent fragment of ice into a glowing comet that reveals the structure of its origin. Each one that appears tells of a distant source untouched since the solar system's beginning. The Oort cloud links the solar system to the broader galaxy. Its outermost edges overlap with the spaces between stars, making it a shared boundary zone, where matter from one system may become part of another. Occasionally, a passing star comes close enough to disturb the cloud. Astronomers estimate that such encounters happen roughly every few million years, shifting the paths of thousands of icy bodies. Some are sent toward the Sun, others are lost forever into interstellar space. One such event in the distant future may even erode the cloud, entirely dispersing its members into the galactic field. Yet for now the balance holds. The gravitational tie between sun and cloud persists delicate but enduring. This remote region preserves a record of early chemistry. The mixture of ices here contains molecules that predate the planet's water, formed in interstellar clouds, carbon-bearing compounds created under faint starlight, and complex organic substances produced by radiation on icy surfaces. These materials represent the building blocks of comets that later delivered volatiles and organics to the young Earth. The Oort cloud, though distant, remains connected to the story of life's raw materials. It is both archive and boundary, a frozen sphere that stores the solar system's earliest history in deep time. Seen from this outer shell, the sun would appear as a small bright star no different from its neighbours. The planets would be invisible, their reflected light too faint to register against the galactic backdrop. Only sensitive instruments aboard a nearby observer could detect the subtle concentration of gravitational influence that marks the solar system's centre. Around it, the Oort cloud would extend as a faint spherical haze of icy nuclei, each reflecting starlight too weak to see directly. The silence would be absolute, broken only by the slow passage of galactic dust and the distant murmur of cosmic rays. This region also defines the solar system's outermost material boundary. While the heliosphere marks the reach of the sun's energy, the Oort cloud marks the reach of its gravity. Together they form nested layers, the inner bubble of solar wind surrounded by the far halo of icy debris. Beyond both lies true interstellar space, a medium of gas, dust and radiation that fills the Milky Way. The sun and its planets drift through that environment, carrying their distant halo with them like a faint shell of memory. The Oort cloud moves as the solar system moves, maintaining its shape across millions of years. Its members are bound not by collisions or contact, but by shared motion around the same distant light. The concept of this region invites a sense of scale difficult to comprehend. From Earth, a signal travelling at the speed of light would need nearly 2 years to reach the inner Oort cloud, and almost a year more to reach the outer edge. No spacecraft has come close. The most distant probes remain far inside the heliosphere, still tens of thousands of times closer to the Sun than this boundary. The Oort cloud remains a theoretical domain mapped through mathematics rather than direct observation, yet its existence completes the picture of the solar system as a coherent structure that stretches from the blazing surface of the Sun to the frozen threshold of interstellar space. In the calm of that extreme distance, change happens slowly, measured in epochs rather than moments. The Oort cloud remains stable, suspended between attraction and release. Its countless bodies circle in quiet solitude, tracing paths that repeat over spans longer than recorded history. From this sphere of ice and darkness, the solar system's outer story continues, carrying forward the silence of its beginning and the gentle pull of the sun that still binds it all together. Moving inward from the Oort cloud, the solar system begins to take form again. The space here remains vast, but the sun's light becomes just strong enough to cast definition on distant worlds. This is the Kuiper Belt, a broad flattened ring of icy bodies orbiting beyond Neptune. It extends roughly from 30 to 50 astronomical units from the Sun, forming a region filled with slow, stable orbits. The bodies here are small compared to planets, but immense in number, billions of frozen remnants from the early solar system, each composed of rock, metal and volatile ices. They are sometimes called trans-Neptunian objects, and together they outline the outer architecture of the solar system. The light that reaches them is faint but steady, a constant reflection from a distant star. The largest members of this region, Pluto, Eris, Haumea, Makemake and others, are round under their own gravity, earning the classification of dwarf planets. Smaller fragments exist in a continuum of shapes and sizes from mountain-scale boulders to tiny grains of ice. The scene is calm, cold, and slow-moving. Each object traces a wide orbit that may take hundreds of years to complete. The sun viewed from here is just a bright point surrounded by a pale halo of scattered light. The Kuiper belt represents a transitional zone between the orderly planetary system and the scattered debris that extends toward interstellar space. It formed from material left over after the planets gathered most of the available matter. In the early solar system, billions of years ago, icy planetesimals formed in this distant region, but never grew into full-size planets. The gravitational influence of the giant planets, especially Neptune, stirred and scattered them, locking some into resonant orbits that remain stable even now. Others were ejected outward or inward, becoming comets or colliding with planets. What survived became the quiet population that defines this belt. Their surfaces preserve the chemistry of the early nebula unchanged by heat or weather. Frozen nitrogen, methane, carbon monoxide, and water ice lie mixed with dark organic compounds produced by cosmic radiation. Over eons, these surfaces have taken on subtle colours, reddish, brownish, or grey, depending on composition and exposure to sunlight. The most famous world of this region is Pluto, once called the ninth planet. It follows an elongated path that sometimes brings it closer to the Sun than Neptune. Its orbit is inclined, tilted out of the main plane of the solar system, completing one revolution every 248 Earth years. Pluto's surface is a landscape of frozen plains, mountain ranges of ice, and thin layers of volatile frost that sublimate and refreeze with the seasons. Its atmosphere is delicate, composed mostly of nitrogen, with traces of methane and carbon monoxide that expand and collapse as sunlight varies. Pluto's largest moon, Charon, is so large relative to Pluto that the two orbit a common centre of gravity in space, forming a binary world. Around them, smaller moons trace quiet paths. This partnership between planet and moon illustrates the balance and diversity of the outer solar system. Beyond Pluto lies Eris, nearly identical in size but more distant, following a highly eccentric orbit that carries it far into the cold. Haumea rotates rapidly, stretched into an elongated shape by its speed and surrounded by a faint ring. Makemake reflect sunlight from a reddish surface coated with methane ice. Each of these dwarf planets is a frozen relic preserving different aspects of early formation. Collectively, they form a gallery of possibilities worlds that might have become planets under different conditions. Their small gravities, thin atmospheres, and icy crusts make them silent witnesses to time. The region also contains countless smaller bodies comets that never left their home, irregular fragments that collided and dust produced by those impacts. Occasionally a collision between two Kuiper belt objects releases fresh surfaces of bright ice, briefly increasing their reflectivity before radiation darkens them again. The distribution of orbits shows patterns. Clusters at certain distances correspond to resonances with Neptune's motion. For example, Pluto and many of its neighbours orbit the Sun exactly twice for every 3 orbits of Neptune, maintaining stability through a gravitational rhythm that prevents close encounters. These resonances create a subtle order within what might seem chaos. The belt, though vast, is organised by gentle mathematical patterns that keep it steady over billions of years. Beyond the main Kuiper belt lies a region of scattered objects stretched into elongated orbits by past interactions with Neptune. Some of these reach hundreds of astronomical units at their farthest points before returning inward. They form a bridge between the Kuiper belt and the inner Oort cloud, connecting the structured and the diffuse. Among them are objects like Sedna, whose orbit extends so far that its aphelion may lie within the realm influenced by other stars. Sedna takes more than 10,000 years to complete one orbit, spending most of its existence in deep cosmic cold. Its discovery hinted that unseen gravitational forces may shape the outer solar system, perhaps even a massive distant planet yet to be confirmed. But whatever its cause, the scattered disk remains one of the solar system's most tranquil and enduring regions, a slow choreography of ice and light. Light itself behaves differently here. Sunlight travels for more than 4 hours to reach this zone, and by then it has weakened to less than 1,000th of its strength at Earth. Shadows are soft. Reflected light has the hue of distant frost. There is no atmosphere to scatter rays, so day and night are divided by silence rather than colour. The stars are sharp and steady, filling the black sky in all directions. Any object illuminated by the sun shines faintly, casting long reflections across its frozen surface. In this stillness, time moves in vast arcs. The Kuiper Belt is also the birthplace of many short-period comets, those that return to the inner solar system again and again on orbits lasting less than 2 centuries. When gravitational interactions with Neptune alter their paths, they can be drawn inward, becoming visible from Earth before returning to the dark. In this way, the belt supplies the solar system with periodic visitors that reveal its distant composition. Each comet carries material unchanged since the beginning, offering a glimpse into primordial chemistry. The quiet persistence of these icy reservoirs ensures that even after billions of years, the solar system remains connected from the outermost darkness to the inner planets through cycles of motion and release. The trans-Neptunian region defines the solar system's shape. It is not a sharp edge, but a gradual thinning of material that fades into the interstellar background. From a distance, it would appear as a faint disk of light illuminated by the sun and speckled with frozen worlds. Within it, the balance between order and randomness continues. Gravity binds each object to the sun, while time erases traces of their early collisions. What remains is an enduring quiet, a slow turning of countless bodies in deep space, each preserving the calm geometry of its path. Inward from here, the orbits of the planets begin. The Kuiper Belt ends not with a boundary, but with a transition, as the population of icy fragments gives way to the gravitational domains of the outer giants. The faint sunlight strengthens, and the colour of the darkness begins to change. The next region is marked by the cold blue of Neptune, where the steady rhythm of orbits continues, but with new layers of atmosphere and cloud. The solar system, still silent, begins to gather structure and light. In the dim outskirts of the solar system, where sunlight weakens into a bluish glow, Neptune circles quietly through space. It is the most distant of the giant planets orbiting the Sun once every 165 Earth years. Its distance is so great that the light and warmth it receives are less than 1,000th of what reaches Earth, yet the planet radiates its own faint heat into the dark. Seen from space, Neptune is a deep blue world wrapped in faint high clouds. Its colour comes from methane in its upper atmosphere, which absorbs red light and allows only blue wavelengths to scatter outward. Beneath those thin clouds, layers of hydrogen, helium and trace gases form a dense dynamic envelope that hides any solid core beneath thousands of kilometres of fluid. The planet's winds are among the fastest in the solar system, reaching speeds of more than 2,000 kilometres per hour. Yet from afar the motion appears smooth and unhurried, the great bands of clouds circling endlessly, guided by a balance of sunlight rotation and internal warmth. Neptune is nearly 4 times wider than Earth, but its mass is concentrated within a dense icy interior. The deep atmosphere merges gradually into a mantle of water, ammonia, and methane under immense pressure, forming what scientists call a supercritical fluid, a state that is neither liquid nor gas. Beneath this mantle may lie a rocky core the size of Earth, hot enough to glow faintly even in the darkness. The planet's magnetic field, tilted and offset from its center, generates complex patterns of auroras around the poles. Because of its extreme tilt, the magnetic field sweeps in broad spirals as Neptune rotates, creating a constantly shifting envelope of charged particles. Yet the field is relatively gentle compared to the fierce radiation of Jupiter or Saturn, allowing its moons to remain undisturbed in stable orbits. The atmosphere's most striking feature, observed first by Voyager 2 in 1989, was the Great Dark Spot, a storm nearly the size of Earth spinning counterclockwise in the southern hemisphere. It appeared and vanished over time, replaced by other dark vortices that formed and dissipated with the planet's changing weather. Unlike Jupiter's ancient Great Red Spot, Neptune's storms are transient, forming from deep convection currents that rise and fall through the methane-rich air. High white clouds made of methane ice crystals drift above them like cirrus clouds on Earth, casting soft shadows across the blue atmosphere. These features move slowly relative to the planet's rotation, giving the impression of serene motion despite the violent winds beneath. Around Neptune orbits a collection of faint icy moons and thin rings, each tracing its path in the planet's pale light. The rings are narrow and dusty, composed of dark particles that may have formed from shattered moons. They contain faint arcs, dense clumps of material that remain stable, due to the gravitational influence of nearby moons. These arcs appear as short, bright segments when viewed by passing spacecraft, showing that even at this distance the balance of gravity and motion creates delicate order. Neptune's moons range in size from small irregular fragments to Triton, the largest and most remarkable. Triton moves in a retrograde orbit, circling Neptune in the direction opposite the planet's rotation. This indicates that Triton was likely captured long ago, perhaps once an independent body from the Kuiper belt. Its capture would have released immense energy, altering Neptune's early system and possibly destroying other moons. Over time, tidal forces circularized Triton's orbit, locking it into a stable path close to the planet. Triton's surface is a landscape of frozen nitrogen, methane, and carbon monoxide sculpted by slow geological activity. Despite temperatures near -230 degrees Celsius, the moon is not completely inert. Voyager, 2 detected plumes of gas and dust erupting from its surface, reaching several kilometers into the thin atmosphere. These geysers, driven by sunlight warming transparent layers of ice, create dark streaks across the pale terrain. The surface shows smooth plains, ridges, and strange patterns of cracked ice, evidence that Triton has been reshaped over time by internal processes. Beneath its crust, a subsurface ocean may still exist, kept partly liquid by the heat generated from tidal flexing. The presence of nitrogen frost gives Triton a soft pink hue under sunlight, and from its surface Neptune would appear immense, filling much of the sky with its deep blue light. The smaller moons of Neptune form a diverse family. Nereid follows an eccentric orbit that swings far outward before returning close to the planet. Proteus irregular and dark circles close in, reflecting little light. Larissa Despina, Galatea, and others lie still nearer, confined within the inner system where Neptune's gravity dominates. Each of them is composed of rock and ice, their surfaces battered by ancient impacts. Together they trace a quiet harmony around the planet, their paths shaped by the same gravitational balance that holds the rings in place. Observations from Earth-based telescopes and from the Hubble Space Telescope have revealed still smaller moons, some only tens of kilometers wide, showing that Neptune's realm remains dynamic and incomplete. The discovery and study of Neptune carry a sense of calm precision. The planet was not found by direct observation but predicted through mathematics. Astronomers noticed irregularities in Uranus's orbit that suggested the influence of another unseen body. By calculating where that influence should originate, they pointed their telescopes and found Neptune almost exactly where predicted. It was a triumph of reasoning that connected invisible motion with tangible sight. Even now, the planet remains a symbol of the solar system's outer order, remote, consistent, and patient in its movement. The light that reaches Neptune takes more than 4 hours to arrive from the Sun. In that time, Earth has turned almost a fifth of its rotation. The planet's year lasts nearly 60,000 Earth days. Its seasons change so slowly that an entire human lifetime would pass without seeing a full cycle. Yet these vast scales of time and distance give Neptune its tranquil quality. The winds may rage, but the overall rhythm is steady. The planet turns once every 16 hours, carrying its rings and moons in a continuous, unbroken motion. In the darkness beyond Neptune, the solar system begins to fade again into the scattered icy bodies of the Kuiper belt. Inward, the next world awaits Uranus, a pale, tilted planet, encircled by narrow rings and quiet moons. Between them stretches millions of kilometers of empty space filled only with faint dust and light. The balance between Neptune's distant storms and Uranus's serene inclination marks the next step inward on the solar system's long, calm path toward the Sun. Moving inward from Neptune, the faint light of the Sun grows slightly stronger, and another ice giant comes into view. Uranus orbits more than 2.5 billion kilometers from the Sun, a world of pale blue and green tones set against the blackness of space. Its atmosphere is similar in composition to Neptune's, composed mostly of hydrogen, helium, and methane, but the planet's color is softer with a milky turquoise hue. The methane absorbs red wavelengths of sunlight and scatters blue but high haze layers, and thin clouds blend the color into a calm, diffuse glow. From a distance, Uranus appears serene, almost featureless, a quiet sphere turning slowly on its axis. Yet its orientation is unique among all the planets. Uranus is tilted on its side by nearly 98 degrees, causing its poles to lie almost where its equator should be. This means that as it orbits the Sun once every 84 Earth years, each pole spends about 42 years in continuous daylight, followed by 42 years of darkness. The result is an extreme but graceful rhythm of seasons that unfold over lifetimes. The cause of this tilt is thought to be an ancient collision in the solar system's early history, when a large protoplanet may have struck Uranus and altered its axis. The impact would have reshaped the planet's internal layers, and perhaps contributed to its unusual magnetic field, which, like Neptune's, is both tilted and offset from its center. The magnetic field produces gentle auroras near the poles, faint glows of charged particles following curved lines through the atmosphere. Beneath the upper clouds lies a deep layer of hydrogen and helium mixed with methane and water, forming a dense, opaque fluid under immense pressure. At greater depths, this merges into an icy mantle of water, ammonia, and other volatiles surrounding a rocky core smaller than Earth. The planet's internal heat is low. It emits almost no excess energy compared to what it receives from the Sun, making it the coldest of the giant planets. Its upper atmosphere can drop below -200 degrees Celsius, a temperature where motion itself seems to slow. Uranus's atmosphere is gentle compared to Jupiter's or Neptune's, with few visible storms or bands. Thin clouds of methane ice form near the upper layers, drifting slowly in winds that can reach several hundred kilometers per hour. Sometimes faint bright spots appear near the equator or poles, temporary storms that rise from deeper layers and then fade away. Because the planet's rotation is retrograde opposite to its orbital motion, the clouds move in unusual patterns across its tilted surface. From the perspective of an observer above the Sun's plane, Uranus seems to roll along its orbit, turning slowly like a spinning top laid on its side. The sunlight glides over its hemispheres in long, smooth transitions, casting half the planet into twilight for decades at a time. Surrounding Uranus is a delicate system of rings discovered in 1977 when the planet passed in front of a distant star. As the star's light dimmed and brightened, astronomers realized that narrow bands of material encircled the planet. The rings are dark and thin, made of small particles of rock and ice, coated with organic material that absorbs sunlight. 11 main rings have been identified, with several faint outer ones extending farther into space. Unlike Saturn's broad reflective rings, those of Uranus are narrow and sharp-edged, often less than 10 kilometers wide. Some contain shepherd moons that help maintain their shape through gravitational interaction, guiding and confining the particles. The rings' faint light reflects only a tiny fraction of what they receive, giving them a subtle grey tone against the planet's turquoise glow. Their structure shows quiet order held together by resonance and motion rather than density or brightness. Uranus is accompanied by a family of at least 27 known moons, each with its own orbit and texture. The 5 largest Miranda, Ariel, Umbriel, Titania and Oberon display surfaces that record billions of years of evolution. Miranda, the innermost, shows immense cliffs, ridges and patchwork terrains, where icy crusts seem to have broken and refrozen. Ariel and Umbriel are smoother coated with frost that reflects faint sunlight. Titania and Oberon, the outermost, are larger and darker, their surfaces covered in ancient craters and rifts, stretching for hundreds of kilometers. These moons are composed mostly of water ice mixed with rock, their temperatures near absolute zero. Like the planet, they orbit in the plane of Uranus's equator, meaning that during the planet's long seasons, some moons may spend years in continuous sunlight or shadow. The entire system moves in near-perfect symmetry, appearing to spin vertically relative to the rest of the solar system. Viewed from the rings, Uranus would dominate the sky as a vast turquoise disk, filling much of the horizon. The sunlight filtering through the thin atmosphere would cast a soft glow across the icy ground. From the night side, the faint reflected light of the rings would appear as pale arcs, stretching across the sky, visible even without a bright sun. The quietness would be absolute, no sound, only the slow rotation of the planet and the distant pull of gravity keeping its moons in rhythm. The scale of motion would make time feel unmeasured, each orbit unfolding slowly, predictably, without disturbance. The discovery of Uranus marked a turning point in astronomy. It was the first planet found with the aid of a telescope in 1781, expanding the known boundaries of the solar system. At the time, its motion was slow enough that it could easily have been mistaken for a star. Over decades, careful observation revealed its orbit and its place beyond Saturn, altering humanity's sense of scale. Later, when its gravitational effects on Neptune were detected, the outer system came into clearer view. The quiet path of Uranus thus became a bridge between what was known and what lay unseen. Despite its distance, Uranus is still influenced by the Sun's energy. The solar wind interacts with its magnetic field, creating faint auroral ovals and shaping the flow of charged particles around the planet. During periods of higher solar activity, the field compresses slightly on the sunward side and stretches into a long tail on the opposite side, similar to Earth's magnetosphere, but on a much larger scale. The subtle dynamics of this interaction reveal that even the most remote worlds remain connected to the Sun's constant breath. In the long arc of time, Uranus continues its motion almost unchanged. Its tilt ensures that each hemisphere experiences a long alternation between light and darkness, while its rings and moons maintain their delicate alignments. The planet's slow, steady rotation defines a rhythm that feels like the heartbeat of the outer solar system, subtle, consistent, and unbroken. From here, the path inward continues towards Saturn, where the quiet geometry of rings becomes visible in full brilliance, and where light, though still faint, begins to shimmer with greater strength. Between the turquoise calm of Uranus and the golden symmetry of Saturn lies the next layer of the Sun's vast and peaceful domain. Farther inward from Uranus, sunlight becomes warmer and brighter, spreading a pale golden tone across space. Here, Saturn moves in its slow, elegant orbit, completing one revolution around the Sun every 29 Earth years. It is the second largest planet in the solar system, more than 9 times wider than Earth, yet less dense than water. From a distance, Saturn appears as a luminous sphere surrounded by rings so thin and vast that they seem almost weightless. The planet's soft colour, creamy yellow with faint hints of grey and brown, comes from layers of ammonia crystals and other compounds suspended in its atmosphere. Below those clouds lie deeper levels of hydrogen and helium swirling in slow currents that stretch around the planet in parallel bands. Though the winds reach more than 1,000 kilometers per hour, the overall appearance remains tranquil, the boundaries between zones blurred by haze. The rhythm of motion is steady, forming a quiet rotation that completes in just over 10 hours. Saturn's rings dominate its visual presence, forming one of the most graceful structures in the solar system. They are composed mostly of water ice mixed with traces of rock and dust, orbiting in an immense disk that spans hundreds of thousands of kilometers, but measures only a few tens of meters thick. From afar, the rings appear solid, but they are made up of countless individual particles ranging from tiny grains to boulders the size of houses. Each particle follows its own orbit governed by Kepler's laws, yet together they form patterns of waves, gaps, and arcs shaped by gravity. The main rings labelled A, B, and C shine brightest, while fainter structures extend beyond them, including the thin F ring and the diffuse D and E rings. When sunlight strikes them at a shallow angle, the ice reflects a soft silvery light that gives the entire system a gentle glow. The rings are dynamic, constantly reshaped by collisions and resonances with Saturn's moons. Some moons orbit within gaps, acting as shepherds that confine ring material and keep it in place. The F ring, for example, is maintained by 2 small moons, Prometheus and Pandora, which travel on either side of it. Their gravitational influence pulls the ring particles into twisted braided patterns that change with each orbit. Other gaps, such as the Cassini division between the A and B rings, are created by orbital resonances with larger moons farther out. These rhythms produce structures that are both orderly and intricate patterns that evolve but remain stable over long timescales. The result is a cosmic balance between motion and stillness, chaos and harmony. The origin of Saturn's rings remains uncertain. They may have formed from the remains of a moon torn apart by tidal forces, or from leftover material that never coalesced into a moon in the first place. Whatever their beginning, they are likely transient on cosmic timescales, slowly spreading and losing material over hundreds of millions of years. Tiny meteoroids constantly strike the ring particles, darkening them with dust and gradually eroding their brightness. Yet for now, they remain one of the most striking features in the solar system, visible even from small telescopes on Earth. Their beauty lies not in permanence, but in constant renewal, the quiet persistence of motion maintained through fragile balance. Beneath the rings, Saturn itself is a world of soft layers and slow forces. The planet's outer atmosphere is composed of hydrogen and helium, with trace amounts of methane, ammonia, and water vapor. Clouds form in bands of different chemical composition and temperature, creating subtle horizontal streaks that encircle the planet. Deeper within, the gas transitions into liquid under pressure, then into metallic hydrogen, a dense electrically conductive layer that generates Saturn's magnetic field. That field is aligned almost perfectly with the planet's rotation axis, creating an environment of symmetry rare among the giants. The field captures charged particles and shapes the radiation belts that circle the planet, though these are milder than Jupiter's. The magnetic field extends outward through the ring plane, influencing how the fine dust behaves, and sometimes producing auroras near the poles where energetic particles enter the atmosphere. These auroras appear as glowing ovals of ultraviolet light, silent arcs that ripple across the polar skies. The energy balance of Saturn is also unique. The planet radiates more than twice as much energy as it receives from the Sun, the result of slow gravitational contraction and the sinking of helium droplets within its interior. This gradual release of heat drives the atmospheric motion, forming long-lived storms and vortices. One of the most famous features is the hexagonal jet stream around the North Pole, a stable six-sided pattern in the clouds that has persisted for decades. It rotates in step with the planet's atmosphere, creating a geometric structure unlike anything else observed in the solar system. Despite its complexity, the motion within the hexagon remains smooth, repeating with gentle regularity. Saturn's appearance changes subtly with the angle of sunlight. When the rings are open, their full width catches light, and the planet glows brighter. When Earth and Saturn align with the Sun, the rings become edge-on and nearly invisible, reducing the planet's brightness. This rhythm repeats roughly every 15 years, creating alternating periods when the rings shine wide and when they nearly disappear from view. The changes are not abrupt but gradual, each stage lasting months as Saturn continues its slow orbit. For observers on Earth, the planet's shifting aspect reflects the larger harmony of celestial mechanics, where geometry and time move together in unbroken precision. Viewed from within the ring plane, the experience would be extraordinary yet calm. Countless icy fragments orbit in silence, separated by vast spaces but held in perfect balance. Sunlight filters through the translucent edges, scattering into pale beams that illuminate the underside of the rings. Shadows ripple gently across the surface of Saturn, expanding and contracting as the rings tilt through the seasons. The gravitational pull between planet and ring particles creates vibrations that travel as waves, each oscillation tracing the invisible mathematics of motion. The entire system functions as a quiet symphony of matter shaped by the same laws that govern every planet, moon, and star. The study of Saturn has connected generations of exploration. The Pioneer and Voyager missions revealed the first close images showing the fine structure of the rings and the variety of moons. Later, the Cassini spacecraft orbited Saturn for more than a decade, observing the planet through changing seasons, flying through the gap between the rings and the cloud tops before its final descent. Cassini's observations transformed Saturn from a distant symbol into a living system, dynamic, balanced, and serene. Even as the spacecraft fell into the atmosphere and burned the data it sent back, preserved the planet's calm grandeur in detail. From a distance, Saturn continues to embody the solar system's quiet rhythm. Its rings shimmer like a frozen river of light, while its moons, each distinct, move in orderly paths. The planet's slow rotation, its gentle color, and its balanced form create an image of harmony that has captivated human curiosity for centuries. Beyond it, Jupiter waits the largest of all, where motion becomes faster, clouds thicker and storms more immense. Yet even there, within turbulence, lies the same underlying stillness that carries through every world circling the Sun. Orbiting around Saturn is a system of extraordinary variety, a miniature solar system within the greater one where more than 80 moons trace intricate paths through the planet's gravity. Each world moves in quiet harmony, with the rings shaping and responding to the same forces that govern the planet's motion. The diversity of these moons reveals the many ways that ice and rock can combine under different conditions of temperature and distance from the Sun. Some are vast, round, and geologically active, while others are small and irregular, little more than captured fragments of ancient debris. Together they form a collection of worlds that illuminate the complex balance of motion, gravity, and light surrounding Saturn. Among them, Titan and Enceladus stand out, one thick with atmosphere and hidden seas, the other small and bright with fountains of water ice. Around these dozens of lesser moons orbit in patterns so regular that their gravitational resonances shape the rings themselves. Titan is Saturn's largest moon, and one of the most intriguing objects in the solar system. It is larger than the planet Mercury, and possesses a dense atmosphere, the only moon known to have one. That atmosphere, composed mainly of nitrogen with traces of methane and ethane, is thicker than Earth's, and creates a permanent orange haze that hides the surface from visible light. Sunlight reaching Titan's surface is dim, as though filtered through thick fog, yet it is sufficient to drive a slow and distant version of weather. Methane behaves here as water does on Earth. It evaporates, condenses, and falls as rain. Lakes and seas of liquid methane and ethane collect near the poles, reflecting the faint light of the distant sun. Rivers and channels carve patterns across the icy plains, shaped by a cycle that has persisted for millions of years. The temperature around -170 degrees Celsius keeps water as solid rock and methane as the main liquid, creating an alien but stable landscape. Beneath Titan's icy crust, a subsurface ocean may exist, composed of water and ammonia, kept partly liquid by heat from radioactive decay. The possibility of such an ocean gives Titan a quiet significance as a potential environment for chemistry that could resemble the early Earth. The Cassini mission, which flew by Titan more than 100 times, revealed dunes of dark organic material near the equator, bright highlands and polar basins filled with hydrocarbons. The Huygens probe, which landed on Titan's surface in 2005, transmitted images of rounded ice pebbles and dry channels before fading in the cold. The data painted a portrait of a world both active and ancient, where the slow processes of atmosphere and erosion create a calm balance between air ice and liquid. From Titan's surface, the sun appears as a small pale disk barely brighter than a star, and Saturn itself is visible only faintly through the haze, a vast shadowed arc dominating the hidden sky. Another moon, Enceladus, is smaller but astonishingly dynamic. Only about 500 kilometers wide, it shines with one of the brightest surfaces in the solar system, reflecting almost all the sunlight it receives. Beneath that reflective crust lies a global ocean of liquid water, kept warm by tidal forces as the moon flexes under Saturn's gravity. Along the south polar region, cracks in the ice allow plumes of water vapor and ice grains to escape into space, creating continuous geysers that feed material into Saturn's diffuse E-ring. These jets rise hundreds of kilometers above the surface, releasing fine particles that drift outward to form a luminous veil around the planet. Cassini flew repeatedly through those plumes, sampling their contents and discovering salt's simple organic molecules and signs of hydrothermal activity on the seafloor beneath the ice. Such evidence suggests that Enceladus may possess the chemical ingredients for life, though at temperatures near -200 degrees Celsius, everything unfolds slowly and without sound. The surface of Enceladus is a mixture of smooth plains, ridges, and fractures, with few impact craters. This youthfulness shows that ice from below resurfaces the Moon periodically. The South Pole is crossed by long fissures known as tiger stripes, glowing faintly in infrared light where internal heat escapes. The continual venting of water vapor demonstrates that even in the outer solar system, internal energy can create motion and renewal. From orbit, the Moon would appear dazzling white against the darkness of space, and Saturn, filling much of the sky, would shine through the drifting plumes like a silent lantern. Beyond these two remarkable worlds, Saturn's moons form an entire hierarchy of quiet companions. Mimas, small and cratered, resembles a frozen sphere marked by a single enormous basin called Herschel, whose diameter is nearly 1/3 that of the Moon itself. Tethys, Dione and Rhea are larger, each showing ancient surfaces carved by impacts and fractures that stretch for hundreds of kilometers. Iapetus, farther out, displays a dramatic contrast, one hemisphere bright as snow, the other dark as coal, the result of material from outer moons coating its surface. This light and dark pattern gives it the appearance of a two-toned marble floating through space. Hyperion, irregular and porous, tumbles chaotically as it orbits, rotating unpredictably while reflecting sunlight from its sponge-like surface. Phoebe, one of the outermost, moves in a retrograde orbit, suggesting that it was captured long ago from beyond Saturn's system. Each of these moons interacts subtly with the rings and with one another. Some occupy orbital resonances that maintain their stability, such as the pairing of Tethys and Dione with smaller companions that share their orbits known as Trojan moons. These configurations show how gravity over time creates patterns of enduring rhythm. Even the smallest fragments contribute to this balance, sweeping ring particles into arcs and clearing narrow gaps. The result is a system of motion so intricate and delicate that it remains stable over billions of years. The view from within Saturn's moon system would be one of immense serenity. The rings seen from the surface of a nearby moon would stretch across the sky in a band of silver-white light, broad and unbroken. Shadows from the rings would drift slowly across the planet's cloud tops, and sunlight would filter through the icy arcs, scattering into diffuse halos. The moons themselves would move silently through this brightness, their orbits perfectly timed, each completing its path without deviation. In this region, day and night blend, gradually governed by Saturn's slow rotation and the soft reflection of light from the rings. The whole system functions as a continuous ballet of ice and gravity. Saturn's moons have reshaped understanding of where activity can persist in the outer solar system. Once thought to be frozen and lifeless, these worlds now reveal that internal heat-liquid oceans and atmospheric processes can exist even at great distances from the Sun. Their rhythms are quiet but enduring cycles of freezing and warming that unfold across geological time. Together they extend Saturn's influence far beyond its visible rings, transforming the space around it into a network of stability and subtle change. As the planet continues its long orbit, this family of moons moves with it, each world reflecting the faint sunlight and contributing to the calm grandeur of Saturn's realm. Beyond them, the next giant waits Jupiter, immense and turbulent, yet bound by the same invisible order that governs even the smallest moon circling the edge of the rings. Moving inward once more, the solar system's most massive planet dominates the next region. Jupiter, larger than all the other planets combined, turns slowly in the pale sunlight more than 700 million kilometers from the Sun. It is a world without a solid surface composed mainly of hydrogen and helium that compress into strange forms under enormous pressure. The planet's diameter is more than 140,000 kilometers, and its gravity is immense, holding dozens of moons and countless fragments of debris in orbit. Despite its scale, Jupiter rotates rapidly, completing one turn in less than 10 hours. This fast rotation flattens the planet slightly at the poles and stretches its clouds into bands that wrap around the entire globe. From a distance, Jupiter appears as a vast sphere of softly blended colours, ochres, browns, creams and muted reds, each marking zones of different altitude and composition. These clouds move in alternating directions driven by deep convection currents that rise and fall through the atmosphere. The contrast between bright zones and darker belts gives the planet its familiar striped appearance, but from close-up those stripes resolve into a shifting tapestry of eddies, ovals and storms that merge and dissipate in continual motion. Jupiter's upper atmosphere is a dynamic system layered with haze and clouds made of ammonia crystals, ammonium, hydrosulfide and water. These materials form at different altitudes, creating bands of colour that vary with temperature and sunlight. Beneath them, the atmosphere thickens into dense layers of gas where pressures become too high for light to penetrate. Within these depths, hydrogen begins to act as a liquid, and deeper still it transitions into metallic hydrogen, a state in which atoms are squeezed so tightly that electrons move freely, allowing electricity to flow. This metallic layer generates Jupiter's powerful magnetic field, by far the strongest of any planet, creating a magnetosphere that extends millions of kilometers into space. The magnetic field traps charged particles, forming intense radiation belts that sweep around the planet and influence its moons. The scale of this field is so great that if it were visible, it would appear larger than the Sun itself when viewed from Earth. The most famous feature on Jupiter is the Great Red Spot, a vast storm that has raged for centuries. This oval-shaped vortex, more than twice the diameter of Earth, rotates counterclockwise in the southern hemisphere. Its reddish colour comes from complex molecules created by sunlight acting on atmospheric chemicals, though its precise composition remains uncertain. Winds within the storm reach hundreds of kilometers per hour, but the overall motion is stately, its edges defined by alternating jet streams. The Great Red Spot drifts slowly westward, shrinking and expanding over time but never disappearing completely. Around it, smaller storms and vortices form, merge and vanish in a perpetual cycle. The entire planet seems to breathe through these motions, converting internal heat into slow atmospheric rhythms that repeat endlessly. Jupiter radiates more energy than it receives from the Sun, the result of gradual contraction and residual heat left from its formation. This internal energy drives convection deep within the atmosphere, causing the cloud belts to churn and shift. Lightning flashes within the storms, illuminating the clouds for brief moments. Some flashes are thousands of times more powerful than those on Earth. The polar regions, where magnetic and solar interactions are strongest, glow with brilliant auroras, ribbons of light generated by charged particles striking the upper atmosphere. These auroras are permanent, glowing constantly as the planet's magnetic field channels energy toward its poles. Seen from orbit, they shimmer in ultraviolet light, encircling the planet like luminous rings. Although Jupiter appears violent, its motion has a calm regularity. The alternating bands of air flow east and west in stable streams that remain constant over decades. These zones mark regions of rising and sinking gas, maintaining balance between gravity, heat, and rotation. The boundary between each band is marked by turbulence, but even that chaos follows patterns of mathematics that repeat predictably. The result is a system both dynamic and stable, a massive engine converting internal heat into ordered motion. To an observer hovering above the clouds, the sight would be overwhelming, yet oddly peaceful, endless layers of atmosphere extending into infinity colours, shifting subtly as sunlight filters through haze and the steady rotation, carrying the patterns beneath like the slow turning of a giant wheel. Beneath the atmosphere, the pressure and temperature rise so high that hydrogen becomes liquid flowing without distinct boundary into metallic form. There is no solid surface, only gradual compression. The core, if it exists, may be a mixture of rock, metal and ice surrounded by fluid layers thousands of kilometers deep. At those depths, the temperature exceeds 20,000 degrees Celsius. This inner heat rises through convection, driving the outer storms and sustaining the planet's weather patterns. Despite its intensity, the planet's internal processes unfold slowly, guided by physics rather than change. Every rotation, every orbit, every eddy is part of a continuous equilibrium that has lasted for billions of years. The light conditions on Jupiter are unique. Sunlight reaching its cloud tops is 25 times weaker than on Earth, creating a permanent twilight even at noon. Yet the atmosphere scatters enough light to fill the sky with a diffuse glow. Shadows are soft and hazy, and colour gradients merge seamlessly from one band to another. From high altitude, the horizon curves dramatically, giving a sense of both enormity and stillness. Each turn of the planet reveals new patterns, but the transformation is slow measured and cyclical. The sense of time stretches. Minutes become part of a rotation that lasts less than half a day, and storms that persist for centuries drift past as though they have always been there. The planet's magnetic field extends far beyond the visible disk, forming a shield that interacts with the solar wind. When high-energy particles from the Sun collide with this magnetosphere, they are deflected or trapped, creating bow shocks and long tails that stretch millions of kilometers. The interaction produces faint radio emissions that can be detected from Earth, a reminder that the planet's influence extends far into space. Jupiter's immense gravity also acts as a stabilizing presence in the solar system, capturing comets and asteroids that might otherwise travel inward. Over time, this gravitational dominance has shaped the distribution of small bodies and may have shielded the inner planets from frequent impacts. In this way, Jupiter's quiet role as a protector adds to its vast, steady presence. From a distance, the planet's colours blend into a soft gradient of cream and copper tones. The motion of clouds gives the illusion of depth, but everything flows within a single endless layer. The sense of scale defies comparison. Storms larger than Earth drift alongside filaments of cloud thinner than air on the Moon. The balance between motion and stability creates a form of visual harmony that embodies the nature of the giant itself, vast, powerful, and unhurried. The rhythm of Jupiter's rotation, the constant flow of its belts, and the pulse of its magnetic field create an impression of cosmic steadiness. Beyond the atmosphere, the planet's moons revolve in ordered paths, forming another system within the larger one. The four largest, Io, Europa, Ganymede, and Callisto, each unique, will reveal new layers of calm complexity. But within Jupiter itself, the pattern is complete, an immense sphere of gas and light turning endlessly in quiet precision, linking the inner and outer regions of the solar system through gravity and time. Encircling Jupiter is a family of worlds so diverse and active that they resemble a miniature version of the solar system itself. More than 90 moons orbit the planet, each held in place by Jupiter's immense gravity and shaped by the tides and magnetic fields that surround it. Together they create a system of quiet order and subtle rhythm where light and shadow move in constant cycles. The four largest, known as the Galilean moons, were discovered in 1610 and remain the most remarkable. Io, Europa, Ganymede and Callisto each display their own geology, chemistry and motion, offering glimpses of the processes that shaped the solar system's beginnings. Beyond them, dozens of smaller moons trace irregular paths, forming a distant halo of captured asteroids and fragments. Within this complex structure, every orbit and rotation fits a pattern, governed by Jupiter's gravity, a harmony of celestial mechanics unfolding in silent precision. Io, the innermost of the Galilean moons, is a world of fire. Despite being more than 600 million kilometers from the Sun, its surface is constantly reshaped by volcanic eruptions, driven not by sunlight, but by tidal forces. As Io orbits close to Jupiter, it is pulled and squeezed by the planet's gravity, and by the combined influence of Europa and Ganymede. This flexing generates intense internal heat, melting rock into magma and forcing it upward through thousands of volcanic vents. The result is a landscape in perpetual renewal, plains of sulfur-frozen flows and tall plumes that rise hundreds of kilometers above the surface before falling back as fine dust. The colors are striking yet subdued in the thin light yellows, reds and whites from sulfur compounds frozen in the cold vacuum. Though violent in nature, the process is rhythmic and stable. Io's surface changes continually, yet the overall balance of motion remains constant, the heat of friction exchanged for gravitational energy in an endless cycle. Farther out lies Europa, a world of water and ice. Slightly smaller than Earth's moon, Europa has a smooth surface crisscrossed by dark lines and cracks, where the icy crust has stretched and broken over time. Beneath that crust, which may be only a few tens of kilometers thick, lies an ocean of liquid water extending perhaps 100 kilometers deep, more than twice the volume of all Earth's oceans combined. The ocean is kept from freezing solid by heat, generated from tidal, flexing, the same process that drives Io's volcanoes, but here gentler and slower. The surface temperature is near minus 160 degrees Celsius, yet the subsurface ocean remains stable, insulated by the ice above. Occasional geysers of vapor escape through fissures, releasing water into space before it freezes and falls back as snow. The evidence suggests that Europa's ocean may be in contact with a rocky seafloor, where hydrothermal activity could create chemical gradients, potentially the conditions for simple life. The thought remains hypothetical, but the physics and chemistry align with possibility. From orbit, Europa's surface appears bright and faintly blue, illuminated by sunlight reflected from Jupiter's clouds. The silence of its frozen plains conceals an entire world of hidden motion beneath. Next comes Ganymede, the largest moon in the solar system, and the only one known to possess its own magnetic field. It is larger than Mercury, with a diameter of more than 5,000 kilometers, and composed of rock and ice in nearly equal parts. Its surface shows two main types of terrain: dark, heavily cratered regions, and lighter grooved areas shaped by tectonic stretching. This duality suggests a history of slow geological activity driven by internal heat. Beneath its crust, Ganymede likely harbours a deep ocean of salty water sandwiched between layers of ice. The moon's internal magnetic field, combined with Jupiter's larger one, creates complex patterns of charged particles and auroral glows near the poles. Ganymede rotates once every 7 days, locked tidally to Jupiter, so that the same face always points toward the planet. Its calm rhythm, immense size, and layered interior give it a quiet majesty, a self-contained world maintaining equilibrium under the pull of the giant nearby. Callisto, the outermost of the four, is older and more tranquil. It orbits beyond most of Jupiter's radiation belts, preserving a surface that records billions of years of impacts. Craters overlap upon craters, forming circular patterns that stretch for hundreds of kilometers. Unlike Ganymede or Europa, Callisto shows little evidence of internal activity. Its surface remains largely unchanged since the early solar system, making it a geological time capsule. Yet beneath that ancient crust, radar data suggest a buried ocean as well, though colder and more stable than those of its inner siblings. The surface, dark and frosted, reflects faint sunlight with a subdued sheen. Seen from space, Callisto resembles a frozen relic, orbiting in quiet dignity far from the turbulence of the planet that governs it. Together, these four moons form a gravitational resonance that links their motions. Io, Europa, and Ganymede orbit in a precise pattern. For every orbit of Ganymede, Europa circles twice, and Io 4 times. This resonance ensures that their orbital periods remain locked, maintaining the tidal heating that keeps Io molten and Europa warm beneath its crust. The pattern repeats with mathematical exactness, keeping the system stable over immense timescales. From a distance, this resonance expresses itself as rhythm, an invisible pulse that coordinates the motion of entire worlds. Beyond the Galilean moons, the lesser satellites continue the harmony. Dozens of small inner moons orbit close to Jupiter's cloud tops, shepherding faint rings of dust. Beyond them, irregular outer moons follow distant inclined and often retrograde orbits, likely captured asteroids or remnants of ancient collisions. Their paths form clusters, each group sharing similar inclinations and distances, showing that the system still bears traces of its formation. The inner moons, such as Amalthea Metis and Adrastea, orbit swiftly within the planet's shadow, reflecting sunlight in short flashes. The outer ones, like Himalaya, Pasiphae, and Calm, wander far beyond the main system, turning slowly through the distant dark. Each plays its part in maintaining the gravitational balance that stabilizes the region around Jupiter. From the surface of any one of these moons, the view of Jupiter would dominate the sky. The planet's immense disk would fill the horizon striped with clouds and glowing faintly under the reflected sunlight of its rings and other moons. Eclipses would occur often as the planet's shadow sweeps across each moon in turn. The light would change, gradually fading to deep copper and returning with gentle brightness. The silence would be complete, broken only by the slow movement of shadows and the faint glimmer of distant stars beyond the planet's halo. Each orbit would bring subtle variations, new alignments, new conjunctions, but the underlying order would remain constant. The exploration of these moons has revealed the quiet power of Jupiter's influence. Spacecraft have flown past and orbited, measuring magnetic fields, sampling radiation, and photographing surfaces covered in frost and rock. Every observation confirms the same principle that motion, even at this scale, follows rhythm and balance. From the molten plains of Io to the frozen oceans of Europa, from the magnetic field of Ganymede to the timeless craters of Callisto, each world demonstrates how gravity shapes energy into calm, repeating patterns. Together they form a microcosm of the solar system itself, diverse, stable, and enduring, each orbiting within the greater harmony of the Sun's pull. Beyond Jupiter's outermost moon, the solar system opens again into wider space. The next region is the asteroid belt, where countless rocky fragments move in quiet paths between Mars and Jupiter. It is there within a zone shaped by both order and absence that the next chapter of this tranquil journey begins. Between the orbits of Mars and Jupiter lies a broad region of space filled with countless fragments of rock and metal, a quiet remnant of the solar system's earliest construction. This is the asteroid belt, a wide ring that encircles the Sun like a faintly luminous band extending from about 2 to 4 astronomical units. The total mass of all its objects combined is less than that of Earth's moon, yet their number is immense, millions of bodies ranging in size from mountain-like boulders to the dwarf planet Ceres. Each one follows its own elliptical orbit shaped by the gravity of the Sun and disturbed gently by Jupiter's pull. The distances between these objects are vast. Despite popular imagination, the region is mostly empty, filled with silent sunlight and dust. The asteroids move slowly, tracing paths that repeat endlessly, preserving the geometry of their positions across billions of years. The belt represents a planet that never formed. In the early solar system, material gathered here under the same processes that built other planets, but Jupiter's immense gravity prevented it from coalescing into a single world. Instead, collisions shattered the growing bodies, scattering debris that settled into separate orbits. Over time, the fragments stabilized into a vast population of solitary travelers. The result is a region defined by balance rather than creation, a fossilized record of what might have been. Many of these objects are primitive, composed of carbonaceous material rich in organic molecules preserving the chemistry of the solar system's beginning. Others are metallic remnants of differentiated bodies whose cores were exposed by impacts. Still others are stony, composed mainly of silicate minerals similar to Earth's crust. Each reflects sunlight faintly spinning slowly through the cold void. Ceres, the largest member, is nearly 1,000 kilometers in diameter and was once classified as a planet before being recognized as a dwarf planet. Its surface is a mixture of rock and ice, with bright spots of salt left behind by briny water that once reached the surface from below. Beneath its crust, Ceres may still contain a layer of muddy liquid preserved by internal heat. It rotates every 9 hours and completes an orbit around the Sun in about 4.5 Earth years, maintaining a steady rhythm within the belt. The spacecraft Dawn, which orbited Ceres for several years, revealed a landscape of wide basins, domes and ridges, evidence of slow cryovolcanic activity that has shaped the surface across immense spans of time. From orbit, the dwarf planet's faint albedo contrasts with the deep black of surrounding space, a single sphere adrift in quiet equilibrium. Vesta, the second largest body, presents a different character. It is a rocky world with a basaltic surface formed by ancient lava flows, marking it as one of the few differentiated asteroids with a layered internal structure. A giant impact at its south pole carved a basin nearly 500 kilometers wide, ejecting fragments that became their own small asteroids and meteorites that have reached Earth. The rest of the belt is filled with thousands of smaller objects, each unique in composition and shape. Some rotate rapidly, others spin slowly or tumble irregularly through space. Collisions among them are infrequent, but when they occur, they create clouds of debris that gradually disperse. The dust produced by these impacts forms faint bands of light observable from Earth's orbit. The zodiacal glow that stretches along the ecliptic at dawn and dusk. The gravitational influence of Jupiter sculpts the belt's structure through resonances regions where the orbital periods of asteroids would synchronize with the giant planet's motion. In these zones, gravitational tugs accumulate, ejecting bodies over time and creating gaps known as Kirkwood gaps. The remaining populations cluster in stable regions between these resonances, maintaining the belt's layered appearance. Over billions of years, these patterns have persisted, showing how order emerges even from chaos. The asteroids' paths are stable, but not static. Some are perturbed into new trajectories that carry them toward the inner solar system. Those that cross Earth's orbit become near-Earth asteroids, occasional visitors whose slow drift connects this quiet region with the dynamic inner worlds. Temperature within the belt varies with distance from around -150 degrees Celsius near the inner edge to colder values beyond. Sunlight filters gently through the sparse dust, reflecting off irregular surfaces and creating slow glints of light. Because there is no atmosphere to diffuse rays, the contrast between day and night is absolute. The illuminated sides of asteroids gleam pale grey, while their shadows remain in complete darkness. Over millions of years, micrometeoroid impacts and radiation darken their surfaces, giving them muted charcoal tones. Despite their desolation, these bodies preserve a memory of the solar system's origin, the composition of the nebula from which all planets formed still locked in unaltered minerals and ices. The asteroid belt functions as a transition between the gaseous outer giants and the rocky inner planets. It marks the boundary where temperature radiation and material density changed enough to divide the solar system's architecture. The same processes that prevented a planet from forming here allowed smaller bodies to remain maintaining a delicate balance that has lasted since the beginning. From afar, the belt would not appear as a bright continuous band, but as a faint veil nearly invisible, except in reflected sunlight. The distances between major asteroids are vast, millions of kilometers separate, even the closest neighbors, yet their collective gravity influences planetary orbits, subtly preserving a quiet symmetry across space. Spacecraft passing through the belt experience no collisions, only the growing sense of scale. Between each asteroid lies a gulf of emptiness filled with sunlight and dust particles. The stillness is total, yet everything moves in exquisite order. The sun's light, taking half an hour to reach this region, illuminates every fragment equally. Shadows rotate slowly, and the weak gravity allows even small impacts to scatter material into temporary clouds that eventually settle back to the surface. Occasionally, a passing comet crosses the region, leaving a faint trail that intertwines with the asteroidal paths before fading into distance. From the perspective of time, the asteroid belt changes little. Individual objects may collide or fragment, but the overall structure remains constant. The belt is both dynamic and eternal, its motion too slow for transformation and too precise for decay. The gravitational patterns that define it extend beyond human comprehension of duration. It is a region where nothing hurries and nothing stops, a zone of balance between creation and stillness. As the journey inward continues, the density of rock and metal increases and sunlight grows warmer. Beyond the inner boundary of the belt, the next planet appears smaller than Earth, but marked by vast deserts, canyons, and ancient volcanoes. Mars stands on the inner edge of this quiet ring, a world of red dust and thin air, where the silence of space gives way to the whisper of wind. But before reaching its surface, the faint belt remains behind a lasting symbol of stability, the calm remnant of the solar system's early attempts to build another world forever unfinished yet enduring. Beyond the inner edge of the asteroid belt, the sun's warmth strengthens, and the faint gleam of distant ice gives way to a world tinted red by iron-rich dust. Mars, the fourth planet from the Sun, orbits quietly at an average distance of about 228 million kilometers. It is smaller than Earth, roughly half its diameter, but its landscapes extend with a grandeur that belies its size. Its surface is a mosaic of deserts, craters, volcanoes, canyons, and polar caps shaped by processes both ancient and ongoing. The thin atmosphere, composed mostly of carbon dioxide, carries only a fraction of Earth's pressure, yet it supports clouds, winds, and dust storms that sweep slowly across the planet. The sunlight here is pale and soft, filtered by the fine particles suspended in the air. Daytime skies glow in shades of pink and apricot, while twilight deepens to violet and grey. Beneath this calm light, the planet turns steadily, completing one rotation, every 24.5 hours a day, almost the same length as Earth's, though far quieter. Mars's atmosphere, though tenuous, is constantly in motion. Seasonal cycles driven by the tilt of the planet's axis, nearly identical to Earth's, create alternating patterns of warmth and cold. Carbon dioxide freezes out at the poles during winter, forming caps that expand and contract with the seasons. When sunlight returns, the frozen carbon dioxide sublimates directly into gas-releasing energy that drives winds across the planet. These winds lift fine dust particles into the air, sometimes forming local whirlwinds, and sometimes enveloping the entire planet in hazy storms that can last for weeks. Despite their scale, these storms move slowly, more like drifting veils than violent tempests. The air is too thin to carry sound effectively, so even when the wind reaches speeds that would howl on Earth, it moves in silence. The surface of Mars tells a story of contrasts, ancient stability, alongside traces of motion. Vast volcanic provinces such as Tharsis and Elysium rise from the plains dominated by shield volcanoes that dwarf anything on Earth. Olympus Mons, the largest, towers nearly 25 kilometers above the surrounding terrain and stretches across an area the size of a small country. These volcanoes formed long ago when molten rock welled up through a crust that never fractured into shifting plates. Without plate tectonics, each eruption built upon the last layer after layer, creating the immense structures visible today. Yet for hundreds of millions of years they have remained dormant, their slopes unchanging except for the slow accumulation of dust. The calmness of Mars's geology is deceptive. Beneath the surface, residual heat and ancient fractures hint at a planet that once flowed and breathed, but now sleeps beneath its frozen crust. To the east of the Tharsis region lies Valles Marineris, a canyon system stretching more than 4,000 kilometers across the equator. It is not the result of flowing water, but of crustal rifting where the planet's surface split and sagged as internal stresses built up. The canyon's walls rise in cliffs several kilometers high, revealing layers of rock that record the planet's early history. Dust carried by the thin winds gathers in drifts along the canyon floor, forming soft dunes that shift subtly over decades. The scale is immense, yet the motion within it is gradual, almost imperceptible. Time on Mars operates at a slower rhythm than on Earth. Processes unfold in thousands of years rather than centuries, preserving forms that seem eternal. Water once played a quiet but profound role in shaping the surface. Ancient river valleys, deltas and outflow channels indicate that liquid water once moved across the terrain, carving paths that now stand as fossilized reminders of a warmer past. Minerals formed in the presence of water remain embedded in the rocks, and in some places layered sediments reveal cycles of wet and dry conditions. Polar caps of water ice still exist, mixed with frozen carbon dioxide gleaming white in sunlight and fading to grey in shadow. Beneath the surface, permafrost extends deep into the ground, and radar observations suggest buried glaciers and possibly briny liquid water in isolated pockets. Today, the planet's low pressure and temperature prevent surface water from lasting long, but traces of its movement remain etched into the landscape like memories of a gentler era. The Martian atmosphere filters sunlight differently from Earth's. During the day, it glows with a diffuse brightness that casts long, soft shadows. At sunset, the sky near the sun turns blue, while the rest fades to warm tones of peach and rose, an inversion of Earth's colours caused by the scattering of light by dust rather than air molecules. These subtle shifts create a landscape of perpetual calm, where changes occur not through sudden weather, but through slow, continuous transformation. Frost forms overnight near the poles and evaporates with the morning light, a daily rhythm as precise as the planet's rotation. Mars also has its own moons, small and irregular. Phobos and Deimos likely captured asteroids orbit close to the planet, their surfaces grey and cratered. Phobos, the larger circle, so near that it rises and sets twice each day, moving west to east across the sky. Its orbit decays gradually, and in tens of millions of years it will either crash into Mars or break apart into a faint ring. Deimos' more distant drifts slowly across the heavens, completing one orbit every 30 hours. Their motions add gentle variety to the Martian sky, reminders of the balance between gravity and time that governs even the smallest bodies. From the surface, the Sun appears smaller than it does from Earth, but still bright enough to warm the thin atmosphere. The temperature during the day may rise to 0 degrees Celsius at the equator, while nights fall below -100 degrees. The cold preserves surfaces for ages. Footprints or wheel tracks can last for years without disturbance. The thin air carries only the faintest whisper of movement, and the horizon, though near, seems endless. To stand on Mars would be to exist in silence, surrounded by vast distances and slow rhythms, a place where time is stretched by stillness. Exploration of Mars has revealed the planet as both familiar and alien. Robotic rovers have rolled across its plains, studying rocks, measuring radiation, and watching dust devils twist across the horizon. Orbiters have mapped its topography in exquisite detail, showing that its quiet surface hides dynamic processes below. Seasonal changes in carbon dioxide, frost variations in atmospheric pressure, and subtle shifts in colour all mark a planet that continues to evolve at its own pace. Each mission adds to a picture of stability, an ancient world still responding slowly and steadily to sunlight and gravity. Mars represents a threshold between the outer cold and the inner warmth of the solar system. Its thin air and frozen deserts mark the limits of habitability as the sun's energy diminishes with distance. Yet within that boundary lies balance, a world not dead but dormant, preserved in equilibrium between past and present. As the journey continues inward, the contrast grows sharper. Ahead lies Earth, covered with oceans and wrapped in air where motion becomes faster, cycles shorter, and the quiet rhythm of the outer worlds yields to the dynamic pulse of a living planet. Moving inward from the red deserts of Mars, the next world glows blue against the darkness of space. Earth, the third planet from the Sun, is a sphere of oceans, clouds and continents held together by a thin atmosphere and sustained by a balance of sunlight and internal heat. From a distance it appears as a living mosaic blue seas, wrapped in white cloud spirals with green and brown continents slowly turning beneath them. Its surface is dynamic, constantly reshaped by air water and the slow drift of tectonic plates. Unlike the silent stillness of Mars, Earth is in perpetual motion, yet it maintains a quiet equilibrium. The planet's orbit carries it around the Sun once every 365 days, while its rotation gives rise to the alternation of day and night in just under 24 hours. Its axial tilt, a little over 23 degrees, creates the rhythm of seasons. Together, these cycles weave a steady pattern that has endured for billions of years. Earth's atmosphere is a delicate blend of gases, mostly nitrogen and oxygen, with traces of water vapor, carbon dioxide, and other compounds. It forms a protective shell that moderates temperature, scatters sunlight, and shields the surface from harmful radiation. Layers within it rise in temperature and pressure, gradients the troposphere where weather occurs, the stratosphere home to the ozone that absorbs ultraviolet light, the mesosphere and thermosphere where meteors burn and auroras glow. The constant interplay of sunlight, air and water shapes the surface through wind, rain, and the endless circulation of oceans. Evaporation, condensation, and precipitation form a closed cycle, redistributing heat and sustaining the delicate conditions that allow life to exist. From orbit, these processes appear as swirling clouds and drifting fronts, their patterns vast but tranquil, each movement part of a greater atmospheric balance. The oceans cover more than 2/3 of the planet and act as reservoirs of both energy and motion. Currents flow across them in immense gyres driven by wind and rotation, moving heat from the equator toward the poles. Waves break gently on coasts and stir sediments on the seafloor, while tides caused by the gravitational pull of the moon rise and fall with remarkable precision. The water's slow circulation connects every region of the globe, blending the atmosphere's chemistry and stabilizing the planet's temperature. Beneath the surface, volcanic ridges mark where new crust forms and deep trenches show where it sinks again, creating a continuous recycling of rock that renews the planet's skin. The soundless churning of these vast systems gives Earth its long, slow rhythm, one that echoes the cycles of its orbit and rotation. The continents stand as dynamic structures of stone shaped by time and weather. Mountain ranges rise where plates converge and valleys spread where they pull apart. Rivers trace their paths from highlands to sea, carrying minerals and sediments that nourish the land. Glaciers creep across polar regions, advancing and retreating with changes in climate. Each movement occurs over spans too long for human senses, yet constant on geological scales. The crust of Earth is not fixed, but flows slowly atop the mantle's convection currents, keeping the surface in perpetual evolution. Volcanic islands rise, erode, and sink again beneath the waves. Earthquakes release stresses built up over decades, adjusting the planet's equilibrium. Beneath all of this motion lies stability, a balance between creation and erosion that maintains the planet's rounded form and steady rotation. The Moon orbits Earth at an average distance of about 380,000 kilometers, completing one revolution every 27 1/3 days. It always shows the same face to Earth, a consequence of tidal locking. Its gravitational pull influences the tide, stabilizes Earth's tilt, and slows the planet's rotation gradually over eons. The Moon's surface is stark and silent, covered in grey dust and impact basins that preserve the history of bombardment from the solar system's youth. From Earth, its phases mark the passage of time. From the Moon, Earth itself appears as a large radiant disk suspended in blackness, its blue and white glow changing slowly as clouds drift across continents. The Earthrise scene from lunar orbit remains one of the most serene vistas imaginable, a living planet ascending over a lifeless horizon, fragile, yet luminous. The interaction between Earth and Moon defines a system rather than two separate bodies. Their shared centre of gravity lies within Earth, but not at its core, causing the planet to wobble slightly as the pair orbits the Sun. Tidal forces stretch the oceans, forming bulges that move around the globe in response to the Moon's motion. The timing of these tides has remained constant for millions of years, creating cycles that influence coastal life and climate. The Moon's stabilizing effect prevents Earth's axial tilt from wandering chaotically, ensuring long-term climate stability and allowing seasons to persist in predictable rhythm. This quiet gravitational partnership has shaped the evolution of both worlds, linking them through motion and light. Within Earth's atmosphere, sunlight creates color and contrast. At dawn, rays pass through long paths of air, scattering short wavelengths and painting the sky in shades of red and gold. Midday light appears white, and twilight fades to deep blue as the sun sinks below the horizon. Clouds reflect and absorb light in endless variation, their forms shifting with air currents that span entire continents. Lightning flickers within storms, illuminating vaporous towers that rise and collapse in minutes. Yet from above all of this appears peaceful, the pale blue sphere surrounded by a thin halo of air, glowing against the black background of space. The contrast between activity below and calm above illustrates the balance that defines Earth's character. The biosphere, the layer of life, is another expression of this equilibrium. Plants, oceans, and atmosphere exchange gases in cycles that regulate temperature and composition. Carbon circulates through rock and air, nitrogen through soil, and living tissue water through every form of matter. Life both depends on and modifies these cycles, creating feedback that keeps conditions stable. Photosynthesis captures energy from sunlight, releasing oxygen that sustains animals, while decomposition returns nutrients to the earth. Over billions of years, this delicate balance has persisted through slow adaptation, turning chemical processes into living systems. Even in sleep and stillness, Earth hums with invisible continuity. Viewed from space, Earth and the Moon form a pair that embodies harmony between motion and stillness. The planet glows with colour and atmosphere. The Moon remains pale and unchanging. Their combined movement through the void follows the same laws that guide every planet, but here those laws create a sense of stability that feels gentle rather than immense. The gravitational dance between them shapes tides' rotation and the steady precession of the axis, maintaining a pattern that will continue for millions of years. Every sunrise, every phase of the moon, every tide is part of that shared rhythm. As the path inward continues, the environment grows more hostile and the air more rarefied. The next worlds, Venus and Mercury, lie closer to the Sun, where heat dominates and clouds burn with acid vapor. Yet even there, within the extremes, balance persists. Each planet follows its orbit with quiet precision, circling the same star that sustains the blue serenity of Earth. Closer to the Sun, the light strengthens and the solar system becomes brighter, harsher, and more condensed. Between the blue calm of Earth and the blazing heat of the inner frontier lie two very different worlds. Venus and Mercury, each reflecting sunlight in its own distinct way. Both are rocky, both lack moons, and both orbit within a region where temperature and radiation dominate. Yet each maintains a separate equilibrium shaped by distance, rotation, and atmosphere. Together they form the final pair of terrestrial planets before space gives way to the immense energy of the Sun itself. Venus, the brighter of the two, is often visible from Earth's sky at dawn or dusk. Its pale golden glow outshines every other planet, a steady, unwavering point of light that never twinkles. Beneath that luminous appearance lies a world hidden by cloud, where the atmosphere is so dense that pressure at the surface is more than 90 times that of Earth's, and temperatures exceed 460 degrees Celsius. The thick envelope of carbon dioxide and sulfuric acid reflects most of the sunlight that reaches it, creating the brilliant visibility that defines Venus from afar. Within that blanket, however, heat is trapped in a runaway greenhouse effect, transforming the planet into the hottest surface in the solar system aside from the Sun. The atmosphere moves in constant circulation. High-altitude winds circle the planet at speeds of more than 300 kilometers per hour, completing a rotation in just 4 Earth days, even though the planet itself spins so slowly that one Venusian day lasts longer than its year. The clouds form smooth layers of sulfuric acid droplets, giving the planet a uniform, featureless appearance when viewed from space. Yet beneath this simplicity lies complexity. Lightning flashes within the clouds and dark streaks appear and vanish in ultraviolet light. The surface below remains mostly hidden, mapped only by radar and landers that survived a few moments in the crushing pressure and heat. It consists of broad plains of volcanic basalt, vast highlands and mountain ranges that rise from the plains like islands in a molten sea. Ancient volcanoes cover much of the terrain, and some may still release gas from deep within, suggesting that Venus, though cloaked in stillness, is not entirely geologically dead. Venus rotates backward compared to most other planets, meaning the Sun rises in the west and sets in the east. Its rotation is so slow that a single day lasts 243 Earth days, longer than its year of 225. This slow turning creates little difference between day and night temperatures. The thick atmosphere distributes heat evenly, producing a planet where every region endures the same unrelenting warmth. Yet from the upper atmosphere, where temperatures are far cooler, the view outward reveals quiet beauty. The sunlight that penetrates the haze scatters softly, painting the clouds in hues of pale gold and cream. Lightning invisible to the eye but sensed by instruments crackles silently within. From the edge of space, Venus appears serene, its violent chemistry hidden behind a curtain of light. Farther inward still lies Mercury, the smallest of the major planets and the closest to the Sun. It is a world of extremes where sunlight floods one side while the other lies in near-freezing darkness. With almost no atmosphere to distribute heat, surface temperatures swing from more than 400 degrees Celsius in daylight to below minus 170 at night. The planet's rotation is slow, taking 59 Earth days to complete a turn, but its orbit around the Sun lasts only 88 days. This creates a curious rhythm in which a single solar day from one sunrise to the next lasts 176 Earth days. The Sun appears to rise slowly, pause, and even reverse before continuing across the sky, a result of Mercury's eccentric orbit and gravitational resonance with the Sun. Despite this strangeness, the planet moves with perfect precision, locked in a stable pattern that has persisted for billions of years. Mercury's surface is heavily cratered, a frozen record of ancient impacts. Vast basins like Caloris stretch across hundreds of kilometers, surrounded by concentric rings of mountains formed by shock waves from collisions in the solar system's youth. Between craters lie smooth plains of volcanic rock remnants of lava flows that once spread across the lowlands. The lack of atmosphere leaves the surface exposed to meteoroid strikes and solar radiation, preserving every feature in sharp relief. Fine dust forms a thin layer of regolith that reflects sunlight with a silvery sheen. During the long night, the sky is filled with stars unblinking and sharp. During the long day, the Sun dominates, appearing more than twice as large as it does from Earth. Shadows are deep and crisp, and the landscape glows with a stark clarity that reveals every ridge and depression. Despite its proximity to the Sun, Mercury maintains a thin exosphere, an almost non-existent layer of atoms knocked loose from its surface by solar wind and micrometeorites. Sodium, potassium, and oxygen drift briefly before escaping into space, replaced constantly by new atoms. The result is a planet with no true air, where silence is absolute, and motion is defined only by light and shadow. Yet even in this quietness, Mercury interacts with the Sun through magnetism. The planet possesses a weak but measurable magnetic field, suggesting a partially molten core of iron. This field captures some of the solar wind, creating miniature auroras, and magnetic disturbances similar in form, but not scaled to those of larger worlds. It is a small echo of the dynamic processes that link all planets to their star. Venus and Mercury, though vastly different, share proximity to the Sun that defines their character. They exist in the zone where solar radiation dominates everything, shaping their orbits, surfaces, and atmospheres. Venus reflects light so strongly that it illuminates night skies on Earth, while Mercury, dark and fast, slips quickly through twilight, visible only briefly before sunrise or after sunset. Both worlds illustrate the limits of habitability, one suffocated by its own atmosphere, the other stripped bare by the sun's energy. Yet even here there is order. Both maintain stable orbits, consistent rotations and predictable patterns of light. Seen from space, Venus glows softly, its clouds forming a perfect sphere of reflected sunlight, while Mercury shines like a polished stone near the sun's edge. Their orbits trace the inner boundaries of the solar system, completing the sequence of solid worlds that circle the star. Together they show the range of possibilities that arise from the same cosmic materials, heat, rock and light, arranged in different proportions. Inward from Mercury, the solar system changes again, not into solid surfaces, but into the dynamic plasma of the Sun's outer atmosphere. Their gas and magnetic energy replace rock and air, and motion becomes constant. The path from the frozen Oort cloud to the molten plains of Mercury now reaches its final destination, the radiant sphere that gives the solar system its structure, warmth and calm luminosity. Beyond Mercury's orbit, the light of the Sun no longer falls as illumination but as force. The space between planets is filled with a constant outflow of charged particles known as the solar wind, a stream that expands outward in all directions from the Sun's upper atmosphere. It is invisible to the eye but defines the true reach of the star's presence. Within this wind lies the inner heliosphere, a vast domain where the Sun's energy and magnetic field dominate every movement of matter. Here the plasma flows steadily at hundreds of kilometers per second, carrying threads of magnetism that twist and fold as they travel through space. The solar wind does not move in gusts but in continuous breath, an unbroken flow that links every planet and particle in the solar system. Even where darkness seems complete, this wind persists, a fine haze of ionized gas connecting the Sun to its distant frontier. The solar wind begins in the Sun's corona, where temperatures reach millions of degrees Celsius. At these extreme levels, atoms lose their electrons and become plasma, a mixture of free ions and electrons that respond to magnetic fields. The gas is so hot that its particles move fast enough to escape the Sun's gravity, accelerating outward along open magnetic field lines. As they expand into space, they cool and slow, but never stop creating an immense sphere of influence that extends far beyond Pluto and the Kuiper belt. This expanding plasma carries with it the interplanetary magnetic field, a spiral pattern formed by the rotation of the Sun. Because the Sun turns once every 27 days, its magnetic lines curve outward like the arms of a vast pinwheel, shaping a structure known as the Parker spiral. Within this structure, each planet moves through alternating regions of magnetic polarity, influencing how charged particles interact with their atmospheres and magnetospheres. Near the Sun, the solar wind divides into two main components: fast streams emerging from open coronal holes and slower streams from regions where magnetic loops close upon themselves. As these flows interact, they form compression fronts boundaries where pressure and density increase. These boundaries move outward through the heliosphere, merging and dissipating as they travel. The overall result is a layered environment that changes rhythmically with the Sun's activity cycle. Every 11 years, the magnetic poles of the Sun reverse, marking the peak of solar maximum. During this period, sunspots multiply, solar flares erupt, and coronal mass ejections send enormous clouds of plasma into space. These events, though violent in scale, follow a predictable rhythm that mirrors the deeper processes within the Sun's magnetic interior. When activity quiets, the solar wind becomes smoother, and the heliosphere expands slightly, breathing in long, slow pulses that repeat through the centuries. Each planet experiences this flow differently. Earth's magnetic field deflects most of the charged particles, creating a protective bubble called the magnetosphere. When bursts of solar plasma strike it, they compress the field and send waves of energy toward the poles where they excite atmospheric atoms and produce auroras. On worlds without strong magnetic shields such as Mars, Venus, or Mercury, the solar wind interacts directly with the upper atmosphere, stripping away gases and shaping long tails of ionized material that trail behind each planet. These interactions, though unseen by human eyes, form a delicate balance between solar output and planetary resistance. Over geological time, this continuous exchange has altered atmospheres, carved magnetic boundaries, and influenced the habitability of planets. Within the heliosphere, dust and plasma coexist in near emptiness. Tiny grains of rock and ice left over from comets and asteroids drift through the solar wind, their surfaces charged by ultraviolet radiation. The magnetic field directs these particles into curved paths, sometimes pulling them inward toward the Sun, and sometimes pushing them outward into interstellar space. Sunlight scattered by this dust produces the faint zodiacal light, a triangular glow visible from Earth's surface just after sunset or before dawn. It is a reminder that even the emptiest regions of space are filled with movement and reflection, the quiet signature of the solar wind at work. The boundaries of the inner heliosphere are not fixed but expand and contract with solar activity. When the Sun is active, the flow strengthens, pushing the edge of the heliosphere outward. When quiet, it retreats slightly, allowing interstellar particles to move closer in. Spacecraft such as Parker Solar Probe and Solar Orbiter now travel through this environment, sampling its density, temperature, and magnetic structure. Their instruments record constant variation-minute fluctuations in speed and direction that reveal the turbulent nature of plasma flow. Yet despite this motion, the overall pattern remains steady. The Sun's influence extends like a slow pulse through space, filling it with energy that fades gently with distance. The solar wind also transports cosmic dust and energetic particles that were born in distant events, supernova explosions, stellar flares, and galactic rays, mixing them with particles from the Sun itself. This combination creates a continuous background of radiation that permeates the solar system. The heliosphere acts as both shield and filter, deflecting many of the highest energy cosmic rays while allowing others to enter. The intensity of this radiation fluctuates, with the solar cycle decreasing during active periods when the magnetic field is strong and increasing when the field weakens. This long-term modulation influences the chemistry of planetary atmospheres and even the climate of Earth, though subtly and over great spans of time. Within this vast field, light behaves differently than it does near planets. There is no atmosphere to scatter it, so sunlight travels as a pure beam, white and sharp, undiluted, until it strikes a surface or particle. Space between orbits glows faintly with scattered dust, but the dominant impression is one of clarity and stillness. From a vantage point within the heliosphere, the Sun appears as a disk too bright to view directly, surrounded by a soft corona that fades into the blackness. Every planet, moon, and asteroid reflects a trace of this light, contributing to the faint collective shimmer that outlines the solar system's plane. Though the solar wind moves faster than any sound could travel, it carries no noise, only pressure and energy. When it strikes magnetic fields, it generates electromagnetic vibrations rather than audible waves. Instruments translate these fluctuations into signals that resemble distant hums and pulses, but in space itself the effect is silent. The flow continues endlessly, expanding, cooling, and blending with the interstellar medium far beyond Pluto's orbit. There, the pressure of the galactic environment meets the solar outflow in balance, marking the boundary of the heliosphere, where the journey that began at the Sun's surface comes to rest. From Mercury outward to the edge of the solar system, the solar wind defines continuity. It connects planets, comets, and dust into a single system, bound not just by gravity, but by motion. Each gust that leaves the Sun carries within it a record of the star's rotation, magnetism, and changing state. As this breath spreads across the void, it maintains the harmony of the system, an invisible tide that never ceases. Beyond it lies the source itself, the star whose radiant energy shapes all else, a sphere of plasma so bright that it hides its own complexity behind the illusion of constant light. The final step inward leads there into the luminous layers where the solar wind begins. At the center of the solar system, the Sun burns with quiet constancy, a sphere of plasma nearly 1.5 million kilometers wide that contains more than 99% of all the mass within the system. It is not solid, but a vast fusion engine where gravity and energy maintain a precise equilibrium that has endured for billions of years. From its deepest core to its outermost corona, the Sun's layers form a continuous gradient of pressure, temperature, and motion, each influencing the space beyond. To the eye, the Sun appears unchanging, a perfect circle of light, but beneath that glow lies a structure of immense complexity and balance. At its heart, hydrogen nuclei fuse into helium under temperatures of about 15 million degrees Celsius and densities so high that matter behaves as both gas and plasma. Each fusion reaction releases photons that begin an outward journey through layers of dense energy transport, moving not in straight lines but in endless zigzags as they scatter from particle to particle. A single photon created in the core may take hundreds of thousands of years to reach the surface, drifting outward through the radiative zone in a slow random walk, transferring energy and momentum as it goes. Beyond the radiative zone lies the convective layer, where conditions change from static diffusion to dynamic flow. Here temperatures drop to around 2 million degrees, and gas becomes less transparent, allowing convection to dominate. Columns of hot plasma rise toward the surface, cool and sink again, forming enormous cells of circulation that carry heat outward in slow rhythmic cycles. These motions generate magnetic fields through the movement of charged particles, creating loops of magnetism that twist and tangle as they interact. The entire convective layer behaves like a fluid ocean of fire, its surface granulated by the tops of rising currents, each roughly 1,000 kilometers wide. These granules constantly shift, forming and dissolving in minutes, yet the overall pattern remains steady, a shimmering texture of light that defines the visible surface known as the photosphere. The photosphere, about 500 kilometers thick, is where the Sun's light escapes into space. Its temperature averages around 5,500 degrees Celsius, producing the warm yellow-white glow seen from Earth. Sunspots, dark, cooler regions caused by concentrated magnetic fields, dot its surface in cycles that mirror the Sun's magnetic rhythm. Each sunspot can span tens of thousands of kilometers and persist for weeks, yet the surface around them moves with continuous calm. The photosphere is not perfectly uniform. Waves of oscillation ripple through it, carrying soundless vibrations that travel deep into the interior. Scientists study these oscillations, a field known as helioseismology, to infer the structure beneath. Above the photosphere lies the chromosphere, a thin layer where temperature begins to rise again. It appears as a reddish glow during solar eclipses and hosts slender jets of plasma called spicules that shoot upward and fade within minutes. Though tenuous, the chromosphere plays a crucial role in transferring energy from the dense layers below to the extended corona above. The outermost layer, the corona, extends millions of kilometers into space. It is far hotter than the surface below, reaching more than 1,000,000 degrees Celsius, though its density is extremely low. The reason for this temperature inversion remains partly uncertain, but it is thought to arise from magnetic reconnection and waves that release energy from the Sun's tangled magnetic fields. The corona is the source of the solar wind, the continuous stream of particles that fills the heliosphere. When observed in ultraviolet light, it reveals loops, arcs, and plumes shaped by magnetic lines that open and close in endless motion. During total solar eclipses, when the bright photosphere is blocked, the corona appears as a delicate halo of pale light radiating outward in smooth filaments, a visible reminder that even the most energetic processes in the solar system can manifest as silence and grace. The Sun's magnetic field governs much of its behavior. It originates from the movement of plasma within the convective zone, where rotation and convection interact to form a dynamo. Over time, magnetic lines twist and become complex, rising through the surface as sunspots and erupting in flares or coronal mass ejections. These events release enormous amounts of energy, accelerating charged particles into space and shaping the structure of the heliosphere. Yet the overall balance remains. After each 11-year cycle, the Sun's magnetic polarity reverses and activity gradually quiets until the next rise begins. This long rhythm is stable, its fluctuations gentle when viewed over cosmic timescales. The Sun, though active, remains predictable, and its constancy sustains the delicate environments of the planets. Light from the photosphere travels through space at nearly 300,000 kilometers per second, reaching Earth in about 8 minutes. It arrives as both warmth and radiation, carrying within it the imprint of the Sun's composition and motion. The color of this light contains all wavelengths, producing white brilliance that, when scattered by Earth's air, turns the sky blue. The energy falling upon the planets drives their atmospheres, powers their chemistry, and maintains their climates. Every reflection, from the pale gleam of the moon to the faint ring arcs of Saturn, begins as sunlight. Even the cold objects of the Kuiper belt and Oort cloud shine dimly with light that once left the photosphere, spreading outward across the solar system before fading into interstellar night. Though the Sun's power is vast, its stability defines it more than its strength. For nearly 5 billion years it has maintained equilibrium, fusing hydrogen at a rate so precise that the balance between pressure and gravity never wavers. This balance will continue for billions more as the hydrogen in its core gradually converts to helium and the fusion region slowly shifts outward. When that time comes, the Sun will expand into a red giant, shedding its outer layers and leaving behind a dense white dwarf that will cool over trillions of years. But in the present age, it remains a steady star, its brightness changing by less than a fraction of a percent from year to year. This constancy provides the foundation for everything else in the solar system. The stable orbits, the predictable cycles, the quiet continuity of energy flowing outward through space. Viewed from the edge of the heliosphere, the Sun appears as a bright, unwavering point among billions of others, yet its influence fills the entire region. The solar windlight and magnetic field that emanate from it form a vast sphere of motion and warmth, extending far beyond any planet's orbit. Every particle, every ray of light, every gravitational pull radiates outward from this center, uniting the solar system into a single structure defined by balance and energy. In this way, the Sun is not merely a source of light, but the governing rhythm of the solar system itself, a vast pulse that moves through the vacuum in silence, steady and eternal, At this journey's end, from the cold edge of the Oort cloud to the blazing heart of the sun, the solar system reveals itself as one continuous whole light flowing into darkness, heat diffusing into cold gravity, holding everything in quiet symmetry. The sun's layers are both its boundary and its origin, where fusion becomes illumination and motion becomes stillness. From this luminous center, every planet, moon, and particle moves in unending orbit, bound together by the steady calm of a single star.